Hello. In this video, I'd like to talk about some of the concepts covered in Chapter 13.5 from the textbook, Applications of the Equilibrium Constant. Just as a side note, to my mind, Zoomdall kind of overlapped concepts into different sections, so I'm dividing it in a way that I think makes more sense to me. Hope it's not too confusing. Anyway, in this video, I begin with the question, what can you do with K? You have a chemical equation, you've written the equilibrium expression, you know the numerical value of K, what can you do with that? Well, the first thing you can do qualitatively is state whether the equilibrium favors the reactants or products. When I say favors, it means at equilibrium at this temperature, do you tend to have, relatively speaking, more of the reactants than products, or more of the products than reactants? Okay, kind of an important question. Well, that lets you can answer that question simply by looking at the magnitude of K. If the magnitude of the equilibrium constant is very, very large, that means that in the equilibrium expression, the numerator is numerically bigger than the denominator. So that means you have more products than reactants. So a large value of K qualitatively means that the equilibrium favors the products. On the other hand, if you have a very small value of K, if it's numerically tiny, that means that at equilibrium, the numerical value of the concentrations of the reactants on the bottom is greater than the numerical value of the concentration of the products in the numerator, so that means a small k favors reactants. Okay? Quantitatively, well, we've seen some things you can do already. That happened in the first video, but here we're going to talk about how we can determine whether a set of concentrations or partial pressures represents an equilibrium position. We actually did that in the first video. We saw that if we have the equilibrium expression, and if we know the numerical value of K, and we have a set of concentrations that we don't know whether represent an equilibrium position or not, we can simply plug them into the expression, and if we get K, we know we're at equilibrium, but if we don't, we know we're not. But now we're going to take that one step further and say, if we're not at equilibrium, state the direction the system will shift in order to achieve equilibrium. And by shift, I mean, will it go in the forward direction to produce more products to reach equilibrium, or will it react in the reverse direction to produce more reactants to reach equilibrium? And to answer that question, we are going to calculate a quantity called Q. Q is the reaction quotient, and for our generic reaction, A plus B in equilibrium with C plus D, Q looks like this. The initial concentration of C raised to the C power times the initial concentration of D raised to the D power divided by the product of the initial concentrations of A and B, each raised to their corresponding coefficients, where the initial concentration means the actual concentration of that component at a specified time, which is not necessarily an equilibrium concentration. It's just what you measure at a given point in time. Okay? So you're going to plug the actual concentrations into the Q expression and solve, and then compare Q to K. If the calculated value of Q is less than K, that means your numerator is too small, your denominator is too big, and you must shift to products or in the forward direction to reach equilibrium. That will increase the value of the numerator, decrease the value of the denominator, and eventually Q will equal to K, and when Q is equal to K, you're at equilibrium. On the other hand, if Q is greater than K, that means the numerator is too big to be at equilibrium, so we must decrease the concentration of the products in the numerator, increase the concentration of the reactants in the denominator, so that means we must shift to reactants to reach equilibrium. Okay. What if Q is equal to K? You're done. No shift, because you are at equilibrium. Okay, so let's see an example of this. We have the numerical value of the equilibrium constant for the decomposition of nitrogen monoxide into its elements. For which of the following sets of conditions is the system at equilibrium? For those that are not, in which direction will the system shift, that is, towards products or reactants, in order to achieve equilibrium? So for each of these cases, we are simply going to begin by, well, let's write out the K expression. We're given moles and liters, so this is going to be a Kc expression, not a Kp expression. So K is simply equal to the product of the concentration of, that's not right. The product of the concentration of N2 and the concentration of O2 divided by the concentration of NO squared. So let's simply calculate each of these. Okay? So for A, Q is equal to 2 moles over 1 liter times 2.6 moles over 1 liter divided by 0.024 moles over 1 liter squared, or 9.0 times 10 to the third. In A, this particular set of concentrations gives me a calculated value of Q that is greater than K, K being 2.4 times 10 to the third. That means the numerator is too big, the denominator is too small, so I must shift towards the reactants in order to achieve equilibrium. In B, I take my moles and liters, and I calculate my value of Q, 0.62 moles over 2 liters times 4.0 moles over 2 liters divided by 0.032 moles over 2 liters, quantity squared, gives me, to two significant figures, 2.4 times 10 to the third. Hey, what do you know? That's equal to K. So that means there is no shift because we are at equilibrium. And then finally, for the final set of moles and liters, Q is equal to 2.4 moles over 3.0 liters times 1.7 moles over 3.0 liters divided by 0.060 moles over 3.0 liters squared. What do you think this one's going to be? Well, plug it into my calculator and I get a value of Q equal to 1.1 times 10 to the negative, or pardon me, 10 to the positive third, which is less than K. That means my numerator is too small, my denominator is too big. In order to achieve equilibrium, I must shift towards the products, or in the forward direction. Let's do one more example. Here's a heterogeneous equilibrium. At 900 degrees Celsius, Kp for the decomposition of calcium carbonate to calcium oxide and carbon dioxide is 1.04. Hey, we've seen this before. This example was in the previous video. And we saw that because this is a heterogeneous equilibrium, we're going to leave out the solids, and we're simply going to write our Kp expression as simply equal to the partial pressure of carbon dioxide. So in each of these mixtures, we want to know that as we approach equilibrium, will the initial amount of calcium oxide, which is a product, increase, decrease, or remain the same? Now, because calcium oxide is a product, we're basically solving the previous problem, asking ourselves, okay, given these conditions, will the system shift in the forward direction to achieve equilibrium, in which case the amount of calcium oxide will increase, or will it shift in the reverse direction to achieve equilibrium, in which case the initial amount of calcium oxide will decrease? This is one of the easiest problems you'll see in this unit because as long as I've got some calcium carbonate and some calcium oxide, it can shift in either direction. And all I really need to look at is the initial partial pressure of carbon dioxide because that is simply equal to Q, because that is the only term in the equilibrium expression. So in A, I've got substantial amounts of the solids and 2.55 atmospheres of carbon dioxide, which is Q. That clearly is greater than K. That means I need to shift towards the reactants to achieve equilibrium, and therefore the amount of calcium oxide will decrease. In B, I've got 780 grams of calcium carbonate, only 1 gram of calcium oxide, but my partial pressure of carbon dioxide is 1.04 atmospheres, which is equal to Q, which is equal to K. So the amount of calcium oxide will remain the same because we are at equilibrium and there will be no shift. In C, I have only 0.14 grams of calcium carbonate and 5 kilograms of calcium oxide and 1.04 atmospheres of carbon dioxide. It doesn't matter as long as there is still some calcium oxide and calcium carbonate for the equilibrium to be established. If my partial pressure of carbon dioxide, which is equal to Q, is equal to K, then there will be no shift because we are at equilibrium, and the amount of calcium oxide will remain the same. Finally, in D, we've got substantial amounts of both solid components, but my partial pressure of carbon dioxide is only 0.211 atmospheres, which is Q, which is now less than K. That means my denominator, it means I don't have enough carbon dioxide to have established equilibrium. It does not meet the equilibrium criteria, so that means I must increase the amount of carbon dioxide by shifting towards the product, and that means that the amount of calcium oxide will increase. Okay. In the next video on the second part of chapter 13.5 and chapter 13.6, we're going to talk about more detailed calculations involving the equilibrium constant. See you then.